Pew pew! I got you, players. My name is Janek. In this video I will show you how to run the Vicuna-13b model locally as a CLI and how to run REST API for it, explain some basic differences between model types, look into VRAM requirements for the models, show you differences in performance for different models and difference in performance of different frameworks to run them. Everything I will show in this video will be done within Windows subsystem for Linux Ubuntu, but it will work directly on Linux. For this video, I am using CUDA 11.7 library. I'm including a link for it in the description. We can start by looking at the difference of various model types. There are currently three popular model types. Vicuna-13b is created and published by LMSYS as a full PyTorch model with floating point 16b weight in the PyTorch format. PyTorch models usually have a naming convention that starts with PyTorch_model followed by hyphen and the number x of x. This is the shard ID of that model. They are split into smaller files to improve the loading to memory. These are called shards. The files end with one of the possible extensions, .pt, .bin, which is a regular PyTorch model, or .safetensors, which is a newer and safer model and it doesn't allow a code execution. These models can be run in the native 16-bit or can be compressed down and loaded in 8-bit precision. There are many different frameworks and libraries that allow you to load and serve these models. Main low-level ones will be the PyTorch itself. The one we will be focusing on today is FastChat, and is the one distributed by LMSYS, creators of the Vicuna model. GPTQ models are pre-quantized models with a lower precision of 4 bits. They usually have the same .bin or .safetensors extension, but they need to be loaded with a separate library such as GPTQ for Llama, AutoGPTQ, or ExLLaMa. I will show you how to run them in FastChat as well, which uses the GPTQ for Llama library. At the end, I will also show how to run the model in ExLLaMa to show speed comparison and touch on a few caveats with this approach. GGML models are specific to the Llama.cpp project. They use the .bin extension. These models allow for various quantization precision and can range from 2-bit to 8-bit. Llama.cpp can be compiled with CUDA extensions to allow for GPU offloading. I will be showing how to run it with the Python bindings that allow to serve the models via REST API. I will be using all of the model types in this video for demonstration, the latest version of Vicuna 1.3. I will include the Hugging Face links in the video description. I already downloaded the original model as well as the GPTQ and the GGML versions quantized by TheBloke. Let's move to the terminal. I prepared a few different directories for all the frameworks we'll use today. Let's start with the LMSYS FastChat. cd into the directory and let's create a virtual environment and activate it. Once the virtual env is ready, we'll install the FSChat from PyPy. Depending on your internet connection, this may take a while. All of this information is available in the FastChat GitHub repo. I will be using it as a reference. I will also link it below. Now that it's installed, we can run it. First, the CLI. Before we do it, I'm going to split the terminal so we can monitor resource usage as I want to show you something. This is my VRAM usage. And this is my RAM usage. This is the CPU load. Let's run the model. I'm using Python 3 FastChat serve CLI with the model path to where I have the models available. Now that while it's loading, first goes to the system memory before it will be moved over to the VRAM. Now that it loaded, let's ask it a few questions and keep an eye on the VRAM. This is a real-time inference of the floating point 16 model. Okay, one more question. looks pretty static and there is no spillover to the CPU RAM, which is both good and bad. Good because CPU offloading would slow it down a lot. CPU RAM is multiple times slower than VRAM. Bad because we don't have any spare memory for inference to expand the network, which also slows it down as it needs to do extra work uh, for video memory management in the background. I'm going to interrupt that now, and for a quick comparison, let's run the same CLI with the same model but loaded in 8-bit instead, and look at the VRAM usage then. For that, we will use the --load 8-bit option. We will use the same option later to launch the API worker. Okay, it loaded and I already asked a few questions so that I can expand the context window. I will ask it a few more questions and we can keep an eye on the VRAM usage. As you can see, that is more dynamic now than the inference is running. It goes up and down by quite a lot, and it can expand depending on the context window. This is because inference requires extra memory for each token of the query, so the longer the context, the more memory is used. We'll look at an external resource that gives a pretty good explanation of how memory usage works for LLMs. I'm putting this link down in the description too, so you can have a look on your own. The most notable thing here is the number 1 megabyte per one token of output. This also relates to the input token within the context window. Llama models by default have context window of 2048. This means that we need at least extra 2 gigabytes of VRAM for the inference. This might vary depending on the compression methods used by the libraries used to serve the model. A good rule of thumb for the VRAM requirement of the model is that the uncompressed 16-bit model will need at least as much VRAM as the size of the model files. In the case of Vicuna-13b, the total model files are 995 gigabytes plus 9.9 plus 6.18 for a total of 26 gigabytes, meaning that they are more than my available VRAM. This is where FastChat and transformers implement optimizations to load it. But chances are that you will get out-of-memory errors when trying to load larger models without having enough memory. Before we move on to launching the REST API, let's first add support for 4-bit GPTQ models. We will use the docs for reference. Note that it says to use different Git branches depending on OS you're running. In my case, I wasn't able to use the fastest inference 4-bit branch on WSL nor on a native Ubuntu box. In both cases, I was getting errors about missing keys in state dictionary. Feel free to try it on your machine, it might be something specific to my setup. We will clone the GPTQ for Llama repo without the extra repository path mentioned in the doc. We'll change directory into it and then switch to the old CUDA brand. Let's try to run the CUDA setup as per the doc. If at this point you're seeing any errors about CUDA version, you will need to switch to version 11.7. I'm including a link to Stack Overflow that explains how to switch CUDA versions. Where it says to install the text table, we'll also need to install TOML and save tensors, as otherwise it will complain that these modules are missing. Now that everything is installed, we can run it, this time specifying the GPTQ model path and extra options specific to the GPTQ model. Important part here is that you need to run the command inside the GPTQ for Llama directory in order for it to have the access to the quantization method. This will be true later if you want to run GPTQ in API as well. I'm going to ask it the same questions as before, and we can immediately see that it is much faster. This is a real speed of the 4-bit inference of the GPTQ model. As we keep asking questions, you will see that the memory usage goes up, and once it does, the model will start slowing down. And once we start hitting the max limit of the VRAM, we will notice it most likely with the next question or maybe the next one after it. We kind of saw that slowdown at the end. I think it will be very visible with this. Okay, there we go. That's the real-time slowdown. This is because the context window grows as the model needs to be expanded in memory and create new paths for the inference. I'm going to stop it, and now we can take a look at running the REST API. FastChat comes with an OpenAI compatible REST server. The server is split into 3 separate parts: controller, worker, and the API server itself. All 3 of them need to be running in order for the API to be usable. I'm going to split the terminal so we can observe all 3 of them. First we run the controller. Then in the other terminals I need to make sure that I'm in the correct location. And run the correct environment. The last window. Then in the second panel we run the worker. We will provide the path for our model, and I'm also going to run it in 8-bit just for the extra speed. And now that it's done loading, we can start the REST API itself. We are running into a problem with the Pydantic library, which after recent updates changed some of its internal settings. For the time being, this can be resolved by downgrading it to older version. So I am going to run pip install Pydantic and forcing it to version 1.10.11. I'm going to encounter the same problem later with the Llama-cpp-python. It is possible that you will not see it on your end, in case if the dependencies for other projects were fixed in the meantime. Now that this is downgraded, we can run again the OpenAI API server. Over here, I'm running it on localhost, but if you want it to be accessible by other hosts in the network, you can change that to 0.0.0.0. And just like that, we have an API host running. Let's give it a quick test with curl and see if it works. I'm going to split the pane again, and I will just curl the API endpoint to query for the models to see if it works. We got the response with the you can see we got the response with the model, and we see that it's running the Vicuna. At this point, we have a working API. We can use the OpenAI Python library to interact with it, or we can interact with it via HTTP directly. I wrote a small script to use the REST API to create a chat, and before I show it to you, listen, right? Like, hear me out. I know my Python is bad. I know, but consider this. I don't care. It does what I want it to do. Feel free to roast me in the comments how bad my Python is. I don't care. It works. Let's have a look at it. This is pretty much a copy of the script from my previous video with some modifications. I'm using AO-HTTP and async IO for the HTTP request. Based on ExLLaMa, that's completely optional. This is just something so that the output is more readable. Date time is just for some statistics that I'm running on like the token generation to calculate how many tokens per second are generated. I'm specifying the API base, which is our local host, and then the chat completions API, which is the OpenAI compatible API, and query for models, so that once we change models, we can still use that script. Headers, which are mandatory for the requests. First, we are getting the model with the async IO. completely horrible way this could be done with URL-lib or requests, but because I already had HTTP imported, that's what I'm using. I'm getting the model name, and then I'm specifying the HTTP payload. Max tokens of 512 for generation, model which we queried for before, and then the list of messages which will be used for chat. Load questions, that should not be here, you can ignore that, that's something that I started working on later. Then we have print response, which will print out the response that we got from the API, and it will also print some statistics about that response. I'm going to go back to that later. This is our main function. I'm specifying retry false. Retry in this context will mean that one of the requests failed due to exceeding the context window, and on that I will be removing one of the oldest messages and rerunning the query again. So this is a forever loop. If we are not in the retry mode, we can then input the prompt, craft our message for the prompt. So we're using the role user with the content, prompt, and response. We appending the message to existing messages list in the payload, creating our session. This is the start time measurement for the time delta, so we can calculate how many tokens per second were generated. Creating session with the payload, and we are waiting for the response. So basically, if the response is successful, we will wait for the output, parse the JSON, and consider it the end of the response for the time delta. Calculate the time delta, parse out the content of the reply from the reply model, get the user statistics from the reply, and then prepare the summary with the print response function that I was showing earlier, and ultimately print it. In case if the response is not 200, so the response is usually 400 baud requests if the context exceeds the maximum context window. I'm going to try to show that how that works. In that case, we are also waiting for the response, just to message, properly finish the request, printing out the errors so that we know what happens in case if it's something else, and then removing, so that we're removing the first entry in the messages list. So basically removing the oldest context, and then we are retrying the same question, catching for any other exceptions, and then also if we're not retrying, then we will expand the message with the message index. So basically we will add our current query and its response to the existing payload. This is something very specific to the OpenAI API, and you wouldn't need to worry about it if you use the OpenAI library. And then finally we run the function. So in the print response, we're getting the content, getting the users and the time delta. We will pretty print the response. Then we will calculate the tokens per second. So basically we're getting the time delta of the completion tokens, probably getting the completion tokens and then dividing it by the time delta. We're creating a summary information that we then later on just iterate over and add to a printable line. It will be like a summary for each of the requests. That's pretty much what the script does. It's very simple and it's very ugly, as I said, but let's have a look how it works. We are the user, and let's start with some of the same questions we had before. Now, because this is not CLI, we will not see the streaming of the output, but we can see that it is definitely being generated. So the GPU is used. You can see its power consumption. And the API will also show the request after it's completed. There we go. So chat completion is finished here, and we should be seeing response over here. Let's try another question. I'm going to skip this part and ask a few questions. Basically, I want to show you how the tokens expand and how it shows the errors. Okay, so now we are approaching the territory where we will be running out of tokens. So our current total tokens of the prompt and the previous response is 1780 2046 and the maximum context length for this model is 2048. So the next response will be giving us an error. There we can see it. So this model's maximum context length is 2048. However, you requested that many tokens, which is too much. So that's why this is removing the context length. This is something to keep in mind if you're going to use this API directly without using the OpenAI's Python library. And also something to note is that with the 8-bit inference of Vicuna-13b, we are getting approximately between 9 and 10 tokens a second. So far, we covered how to run Vicuna on your GPU from FP16 and GPTQ models. Let's now have a look on how to serve the GGML model. We are going straight for the API to the Llama-cpp-python project. Let's first create new virtual environment for it. Source it. This will be as simple as running the pip install from the GitHub documentation. Copy that. You need to put the quotation mark around the package name. This is because Linux will interpret square brackets as a test comparison. So we can run that now. So once it's installed, it should be as simple as running the server command afterwards. But remember that I mentioned that pedantic error before, which we'll see now again. I have the command to run it. And there's this again, the pedantic one. So to fix this again, I'm going to downgrade it to version 1 just like before. And afterwards, we can rerun the server command. For this, keep in mind that the model needs to point directly to the bin file, not the directory like before. We need the bin. I'm using the smallest model in this example so that it loads faster, but keep in mind that the response quality will also be lower. And just like that, a few moments later, we have a working API. Let's test it with our chat script. Works like a charm. Give it another question. Cool, so it works fine. This is definitely the easiest method with least hardware requirements, as it can run on just about any CPU. Finally, we'll have a look at the ExLLaMa. The instructions mention prerequisite to install specific version of Torch, but this will force the use of the latest CUDA. So for now, we'll skip this step and just install the Torch from requirements text. As always, remember to create the virtual env, activate it, let's it on the ExLLaMa and cd into it. Afterwards, we'll install all the requirements from requirements.txt. There are a few examples available in the repo. We'll look specifically at the example chatbot. We'll run it with our GPTQ model and see how it performs. Over here, we're specifying our GPTQ directory, our username, and the prompt template, which is provided in the repository. Okay, it loaded up with the prompt. Let's give it something to write now. I'm going to run the same questions as before. And as you can see, this is a real-time inference speed. As you can see, it is really fast, but you might have also noticed that the responses are much shorter than anything else that's used by FastChat. This could be due to the model inference settings like the temperature and the top K, top P, repetition penalty, and so on. In my previous attempts, I tried to match these settings to the default ones used by FastChat, but I still received really short responses. I'm not sure what else might be a factor here. If you know, leave me a comment. I will appreciate it. But look at that speed. I'm going to try to find the comparison side by side, the 4-bit inference speed with FastChat, and overlay it on the screen. This is just blazing fast. There are two other things to keep in mind about this project. It is still in early development, as the author mentions on its GitHub page, and it doesn't work on older video cards. I tried running it on a Tesla P40, but it doesn't support that old of an architecture. Another thing is that currently it doesn't provide an OpenAI compatible API. There is an API example, the example FlaskPy, which provides a bare-bones structure for an API that you could use, but it also needs certain variables to be modified. For example, the model directory, and so on. I'm looking forward to seeing how this project evolves over time, as it is really impressive how fast it is. I hope you learned something today. Go play around with it and have fun. Bye.